The clock is ticking on climate action. We stand at a critical juncture where decisions made today could determine the trajectory of future generations. While policies shape our collective response to climate change and sophisticated models could provide the scientific foundation for these decisions, there's a fundamental problem. We're drowning in data we cannot understand. The key factor in play here is climate uncertainty, meaning that the behaviors of the Earth's systems might change in ways we cannot foresee due to global warming. Scientists have concluded that in this case, to identify robust policies, we must simulate not one, but thousands of possible scenarios together and navigate the data clouds to find the best solutions. But here's the problem. These data clouds are high-dimensional, large-scale oceans of data that the most intelligent can't fully process, and hence a dangerous gap between science and policy, leading to oversimplified approaches to humanity's most complex challenge. Our solution is Envision, a four-layer framework capable of translating complex climate data into actionable policy insights. The sampling layer creates initial scenarios. The GCAM layer runs climate simulations and produces the data cloud we need. Then the topological data analysis layer extracts non-trivial structures from the data. Finally, large language models translate these mathematical findings into accessible insights characterizing the key trade-offs and decision landscapes for policymakers. In sampling, we develop frameworks ensuring spatial coverage while preventing the distortion of underlying data structure. In GCAM, we selected output parameters and anticipated emergent system behaviors to focus our analysis on. In topological analysis, recognizing that traditional structures like tori and Mobius strips don't correlate strongly with climate system dynamics, we developed 5 climate-specific topological objects. In LLM integration, we developed prompt engineering frameworks ensuring the model provides descriptive rather than prescriptive information, maintaining scientific objectivity while maximizing policy relevance. So what are the results? First, we tested Envision on the log-coupled terror system, which is a simpler model with analytical solutions, to validate our framework's accuracy. And the results? 92.3% accuracy in identifying system dynamics. Second, we applied Envision to the full GCAM system to explore dynamics beyond current knowledge. The system successfully confirmed the long-standing policy observations, quantified key relationships, and provided novel large-scale insights into climate policy landscapes. But why Project Envision? Well, we're living through a critical lock-in phase for humanity. And the decisions we make in the next decade will fundamentally determine whether we achieve sustainable development or face civilizational collapse. Yet paradoxically, as our models become more and more sophisticated, the gulf between scientific capability and policy application has widened dramatically. Project Envision also stems from my personal experience, combining both mathematics, including topology, as well as AI research. In the meantime, I'm also a UN youth delegate, having worked in science policy interface. This rare skill set provides me with a unique opportunity to contribute to building a bridge between science and policy. And I didn't do it alone. Key collaborations shaped this journey. In January, studying complex systems in Shenzhen inspired my proposal to use topology to detect chaotic ecological system behaviors, leading to an ongoing testing with complex system analysis. At the UN HLPF for SDGs in July, insights from ISC representatives and UNEP complex system analysts crystallized 2 principles that guided Envision's development. Scientists must become brokers between science and policy, and science must remain descriptive, not prescriptive, when providing policy insights. Moving forward, we'll refine the mathematical foundations through experimentation with diverse complex systems while conducting user testing at UNEP and ISC to continuously improve the interface and expand our impact. And what makes this project uniquely urgent is the convergence of 3 factors. First, we have mathematical tools sophisticated enough to extract meaningful patterns from high-dimensional data. Next, we have AI systems capable of translating complex mathematical insights into human-accessible language. But most importantly, we have a rapidly closing window of opportunity to apply these tools to humanity's greatest challenge. And at this critical moment in human history, we cannot afford to let valuable climate insights remain trapped in incomprehensible data clouds. Envision represents a blueprint for bridging the science-policy divide, ensuring that our best scientific understanding can inform our most crucial decisions. And as David Hilbert once said, we must know, we will know. For the sake of humanity's future, we must transform that knowledge into action. Thank you.